Okay, we're going to learn about one of my favorite topics in algebra, which is using matrices to solve systems of linear equations. And first of all, we need to learn how to write a system of linear equations as a matrix equation. So what we're going to do is we're going to write a matrix that contains all the coefficients of our variables, multiply that matrix by the variables themselves, and set that equal to the constants. Okay, so here's our first equation, and the coefficient of x is 1, and the coefficient of y is -1, and the coefficient of z is 1. The second equation, the coefficient of x is 2, the coefficient of y is 1, the coefficient of z is -3. And finally, in our third equation, x is coefficient is -3, y's is 2, and z's coefficient is 1. Okay, so we're going to write this variable matrix right here, x, y, z, and then over here we write the constants, 12, 6, 18. Now hopefully you remember how to do matrix multiplication, so remember that as I multiply each of the terms in this first row by the terms in this column, it will equal the first row, first column terms. That'll be 1x minus 1y plus 1z equals 12. Which is our first equation. So now you see how this matrix equation is exactly the same as this system of linear equations. Okay, next, the multiplicative identity matrix, which we usually write as I sub n, is a square n by n matrix with ones all along the main diagonals here and zeros for all the other elements. So if we're working with numbers, say any number, a times 1 is that same number, and 1 is called the multiplicative identity. Well, here the same thing happens with identity matrices. If I multiply any, say, 3 by 3 matrix by this matrix, I'm going to end up with the same matrix I started with. It works just like the number 1 works with numbers. So now we're ready to define an inverse of a square matrix. So if we let matrix A be a square n by n matrix, then if there exists a square n by n matrix that we call A inverse, that's what that little -1 means, such that when I multiply A and A inverse together, I get the identity matrix. And if I multiply A inverse times A, I still get the identity matrix. Then we can say that A inverse is the inverse of A. So this kind of works like numbers, right? So what's the multiplicative inverse of 2? Well, it's 2 to the -1 power, because that's really 2 times 1/2, which gives us the multiplicative identity 1. So you could kind of think of the same thing happening with inverses. Now there is a way to figure out inverses by hand, but it's really tedious, and we all have graphing calculators these days, so I'm going to show you how to do it using a graphing calculator. And the first thing you're going to do is hit alpha and then hit the y equals to get F1, and then we're going to use our arrow keys to go over to matrix. And you'll notice that this lets me choose how many rows and how many columns I need. So this is a 2 by 2. So I use my arrow keys to highlight 2. I hit enter, enter, and then go use my arrow keys to get down to OK, and hit enter, and it automatically gives me a 2 by 2 to fill in. So I'm going to hit 3, then use my arrow key to get 1, arrow down and arrow to the left, put in 2, arrow over, put in 1. Now I'm going to arrow outside the matrix, and I'm going to hit my x to the -1 button. That's my inverse button for a matrix. And I just hit enter, and there it is. Well, come here. Oh, 2 showed up. Hang on a minute. Okay, so I found the inverse of this matrix. The inverse of this matrix is 1, -1, -2, 3, and if we multiply them together, we should get the identity matrix. So let's just test that. I'm going to go alpha F1, and I'm going to arrow over to matrix. I'm going to put in my original matrix, 3, 1, arrow down, put in 2, 1, and then I'm going to go function F1, arrow over to matrix again, and I'm going to put in the inverse that we just calculated. So it's going to be 1, -1, arrow down, -2, 3, and we should get the identity matrix, and we do. There it is. So why do we worry about inverse matrices? Well, we can use them to solve systems of equations. And so let's convert this system of equations to a matrix equation. So it's going to be 2, 4, 1, 1, 1, -1, 1, 1, and there's no z, so I have to put in the 0, okay? And that's times x, y, z equals our constants, -5, 7, 0. And solving for x, y, z, x, y, z is equal to the inverse 2, 4, 1, 1, 1, -1, 1, 1, 0, inverse times our constant matrix. Now you have to do it in this order, okay? Because remember, I have a 3 by 3, and here I have a 3 by 1, and the columns of this matrix have to match the rows of this matrix, okay? So it won't work to do the constants times the inverse. It has to be the inverse times the constants. Okay, so when we're at this point, time for our calculator. And I'm going to put this in just the way it looks, okay? I'll move it over here. How's that? Okay, so I'm going to go alpha F1, arrow over to matrix, and this time I need a 3 by 3. Okay, so I'm going to arrow over to 3, arrow down to OK, and I'm going to fill in my coefficients. 2, 4, 1, 1, 1, -1. This is exciting, isn't it? 1, 1, 0. And remember, I want to get the inverse of that, so I hit my x to the -1 button. And then this matrix is a 3 by 1, so I'm going to go alpha F1, arrow over to matrix, and arrow up to 3 by 1. 3 rows, 1 column. Arrow down to OK. Enter. And I'm going to put in -5, 7, and 0 is already there. And I arrow outside of the matrices. I hit enter. Voila. X is -1, Y is +1, and Z is -7. Now the cool thing about this is that using this technique, we can solve a system of any size equations we need. Say 10 variables, 10 equations. It doesn't matter how many equations we have and how many variables. We can use matrices to solve them. So it's a really, really powerful technique. So here's our final answer. Our x, y, z matrix is equal to -1, 1, -7. If you wanted to write that as an ordered triple, it'd be -1, 1, -7. All right, have fun with matrices.